Weather is impacting everyone, not just every business or every organization or a country. It impacts every human being.
People underestimate the size and scale of weather data. Remember, we're talking about Earth here. Think about the dimensionality of that scale of data. It's massive.
It's very challenging for a group of atmospheric scientists who see challenges in weather prediction and want to address them to do every part of that equation on their own. We're still dependent on that traditional set of initial conditions released by the operational centers once every 6 hours. A lot can happen in 6 hours, right? Think if we're monitoring a storm, or monitoring inputs into a watershed, are we going to have a massive burst of precipitation lead to flooding?
A lot of the globe doesn't have real-time radar coverage or weather observation coverage. And the reason that's important is a lot of weather events develop over the oceans, and we're unable to observe them until they get close enough to land to be observed by ground-based radars, or enough time has passed that it's not real-time enough to take any action.
Your mind starts to spiral as you think about just a single weather event, all of the different pieces that have to come together and all the different things that are influenced by that. I have such a hard problem looking at something out in the wilderness, looking at the mountains and seeing, freshly fallen snow, and thinking about what was the weather pattern that led to that? How is the radiative balance being changed? Where did the moisture come from? Where did the dynamics come from that drove the storm? With how rapidly machine learning has progressed in recent years, it seems like every day you see a new model being released in some sort of AI capacity. And that can kind of feel like the norm. And the reality is that, at least in weather prediction, any gains, any improvements are really hard fought. So historically, weather forecasting came about in the early 1900s, largely for prediction of operational activities. And it's only really been the last 2, 3, 4 years that we've seen AI-based weather prediction models actually start to exceed the skill of those models that had anchored our operational weather prediction for the last 70 years or so. Tomorrow.io is charged with distributing weather insights and weather data to its broad customer base around the globe. We do that through a platform and API, Tomorrow.io's resilience platform. And that's really meant to be the type of place where a customer can come and they can set up their insights that are going to be driving their business operations. If we think of a globally distributed network where you have to maintain a platform that's the best weather predictions possible at any point in the globe, underneath the hood, there's many different types of models that need to run, right? There's nowcasting ones, there's forecasting ones. You need real-time observations. Some places have radars, some are dependent only on satellite information. And so for us to be able to maintain that resilience platform that delivers those insights, we have to have on our side scalable solutions that allow us to deploy containerized applications that run each of those weather models.
We run our AI models on Azure, and we use NVIDIA's GPUs in the processing of what we're doing. But the partnership is much bigger than that. With NVIDIA, we've had a collaborative process around research and development of modeling. So the Tomorrow approach is a multi-model approach, meaning that on one hand, we develop our own AI models. On the other hand, we're trying to use everybody's models because we understand that eventually, in the long run, no model will be superior to the rest of the models in a lasting way. It's a constant improvement of a community. And what is really important is to operationalize this model, putting it in the right context for a business outcome, and at the same time to make sure that these models are leveraging the best data that is available out there, because without data, the model is not really useful.
We have to kind of break uncertainty into two forms, right? There's intrinsic predictability and practical predictability. And intrinsic is kind of what you might think of as the chaos and the butterfly effect and all these pieces where a thunderstorm that's evolving, like it has things that are just inherently unpredictable in nature. And then we have practical predictability on the other side, where the limitations in our predictive skill, how far out we can accurately say what the weather's going to do for the next hour, day, week, are really limited by things like our computational power. So when we're thinking about some of the large developments that we've seen in computational ability to emulate the physics of the atmosphere in a much more economical way, at Tomorrow I/O, a lot of our interest is to be able to bring those new developments, new code bases to market and to be able to have a positive impact on our customers. The way that we did that was the development of our focus model. And this is really grounded in the open source code that exists on Earth 2 and Physics Nemo from NVIDIA. And we've kind of tailored it and retrained the model specific to some of the use cases that we have. And it was an opportunity for us to go and look at what are the fundamental limitations of predictive accuracy for our customers. NVIDIA Earth 2 on Azure has been fundamental to our development at Tomorrow I/O for being able to access different physics-based models or physical models of the atmosphere, right? And different ways that NVIDIA's researchers have developed to be able to represent the Earth and different ways to improve predictions, both on short meteorological scales as well as at climate scales.
Thanks in large part to the Earth 2 team that's helped us be able to rapidly take an observation of Earth and post-process it at speeds that we've never seen before and deliver it as an insight built on top of the Azure stack that allows us to be able to make data more valuable worldwide across governments and enterprises, as so many different entities have different types of ways to observe the atmosphere.
One of the really interesting things that we've seen happen in the last few years is the release of NVIDIA's CorrDiff model. It's corrective diffusion, and it's a really different approach for being able to mitigate some of the traditional challenges with grid resolution. And think of, the last time you were watching a thunderstorm develop. Ahead of the storm, before it even started raining, you feel this huge gust of wind come at you. And the temperature drops suddenly. It's a real big environmental change. And it's sort of the interaction of all these different physical processes associated with how did that storm form and what happens when the precipitation starts to fall. The evaporative cooling leads to this outflow of winds and stuff like that. Effectively, CorrDiff can learn to emulate all of those physics just from seeing lots and lots of data, lots and lots of representations of that kind of interaction happening.
What it created for us was a foundation to be able to leverage the GPUs that are existing in the Azure pipeline that we run all of these models on top of through our focus architecture, which is effectively what all of this has led to. It's enabled us to be so much more flexible as we deploy new models on our Azure stack for different clients that have tailored configurations for their use case, so that our scientists can chase the problem and to be able to capture severe events because we're able to expand the probabilities of which we can predict. It's really opening the arena for risk management of our customers.
When we started the company, we had zero intentions of building satellites. We were actually a software-only business. And then I think very early we understood that the holy grail is really the lack of data. At some point we said, it cannot be solved from the ground. Maybe we need to look at space. So what we did as a company, we started thinking about what kind of satellites we could use just to find out that no existing satellite can actually create the data that we need everywhere. So you have to come up with new satellites.
Developing a satellite used to take 10 to 15 years, but they were also designed to last for 20 years. Technology is moving so fast and space is so accessible now, we can develop one satellite for one instrument that might only last 2 or 3 years, but you could tech refresh right after that, and it's affordable to do that. Our satellites are pretty unique because of the coverage that we get and the size that they are. This instrument scans and sees a really wide swath width, and the size of the instrument themselves is a 6U size CubeSat, which is about this big, about the size of a loaf of bread. Think of that up in space with 12 of them being able to see the whole globe is pretty incredible. And that really all has to do with how the instrument spins and scans and observes the Earth. Our Generation 1 constellation is a hybrid constellation, meaning there are 2 different types of instruments. So we have 2 radars and then a constellation right now of 7 microwave sounders that we're building all the way up to 18 microwave sounders.
All the sensors that are part of our constellation, right, they generate data that is input to models. The more data that you bring in, and the higher resolution of that data, both in space and time, more just begets more. AI is showing us that you can break that paradigm by going to models that are learning from physics-based models and are able to more efficiently ingest large quantities of data.
Our objective is to get to that sub-hourly revisit rate of global weather data, meaning that within an hour, we will have observed every single point on the globe and be able to feed that into forecasts.
Our mission comes into a place where we see significant potential to fill massive data gaps. Microsoft and NVIDIA are developing novel technologies that empower and accelerate the ability for AI to change the industry.
With Microsoft and NVIDIA, we've been able to put up an offering for every meteorological agency in order to modernize its infrastructure. So think about a country that doesn't have a reliable infrastructure. Now, with tomorrow running on Azure and using NVIDIA's infrastructure, we can modernize a meteorology agency capability overnight.
At my core, I'm an atmospheric scientist, right? I'm not a software engineer. Most of the new utilities and new capabilities that we see in the machine learning world aren't native to me, right? I learned about clouds and rain and all these things that are really true to the way that I work and think about problems. And for me to grab a containerized application and be able to modify it to do the things that I want to see it do as a meteorologist rather than as a software engineer. And then to be able to, deploy that into training and iterate through many different experiments about traditional sources of forecast uncertainty and error, and being able to connect them to the GPUs on Azure that allows us to really meet the end goal of delivering better weather insights without having to develop every piece of that on our own.
These are decisions that we really want to focus on because those decisions are saving lives, they reduce accidents, they improve employees' safety, they improve the bottom line, the top line sometimes. We're doing something that every citizen in the world is going to benefit from and is already benefiting from. It's a huge privilege.